The Robotic Pole Inspection Collar, also known as RUPIC, by Group 7. Here are the project goals. To create a robot that can safely ascend and descend a wooden utility pole under full load. Be operated by and send test results to mobile application on a user's device. Perform a simulation of the hammer test that is performed by linemen on a utility pole. Use audio analysis on the hammer strike to determine pole health. Dynamically tension on the utility pole to account for tapering pole diameter as well as various pole sizes. Store results of testing in a database to be viewed later by the user. Moving on to the project requirements/constraints. The final design should have a total weight less than 50 pounds. Run for 1 hour continuously off drill batteries typically carried by linemen. Be able to be transported in large suitcase on the back of an FPL truck seen below. Run in 5 minutes after installation begins. Fit on and test the given range of utility poles maintained by FPL. Determine pole health using a non-invasive or minimally invasive technique. Lastly, be weather resistant. To continue this, it should stop before it encounters telecom facility/FPL neutral. Work around risers. Display inspection results. Display robot health. Operate using a controller of some sort. Have a tensioning mechanism in the event of power loss to prevent damage to the robot. And lastly, have a kill switch for safety reasons. To accomplish this is the project design. It should consist of 2 separate collars so that one can rotate around the other. Have a separate module that can attach to the main body that performs hammer test on pole. Use linear actuators and feedback control to properly establish and maintain tension on the pole. Use an Android mobile application to send commands to the system and display results from the hammer test. An audio analysis program that will take a recorded hammer strike and determine if the strike was good or bad. And it will to store results in a database that can later be used to create a trend for pole health or confirm system accuracy. Here are the revisions for the collar design. The first revision focused on 4-section assembly of both the inner collar and outer collar sections with 3D printing as the main manufacturing method, which was changed in the second revision because it focused on a new restriction regarding the printer bed size for recommended 3D printer, courtesy of the lab director. Revision 3 focused on a new restriction regarding a change from 3D printing to laser cutting manufacturing method. The RUPIC collar had to be sliced horizontally and exporting all these layers as a DXF file. The final revision, revision number 4, focused on organizing the 5mm slices of the RUPIC collar to sections for ease of use of the laser cutter operator. Here we can see revisions 1 through 2, because revision 1 and 2 were identical in design but differed in dimensions due to an update on which 3D printer bed we could use at the time. Here you can see the outer collar section, which was supposed to rotate around the stationary inner collar sections on the right. Here is revision 3. Revision 3 was an update of the first 2 revisions but sliced the original design every 5mm distance horizontally. Here you can see the updated design and the many layers that it would have on the left, and all of the layers basically turn into DXF files. And in the final revision, revision number 4, doesn't differ from the design of revision 3, but organizes the DXF files into a couple identical sections for ease of use by the laser cutter operator. Examples of new organized sections seen below. Here you can see the inner collar sections, more inner collar sections with a different section of it, and then the last one shows outer collar sections. Here's the collar design implementation. Firstly, we wanted to have an inner collar sections and outer collar sections. The idea behind this, separating the collar into 2 sections, rotating the outer collar section in respect to the stationary inner section. This would allow for any attachments like the hammer test subsystem to perform operations around the whole perimeter of the wooden utility pole. Secondly, having an arc length of 270 degrees instead of a full circle. Purpose of this 90-degree gap is to allow attachment to a pole through the empty gap. The absurd size of the collar in comparison to the previous team that worked on this project. The size increase of the collar was due to the various pole sizes that the collar would need to fit around. So during testing, we tested these couple testing principles, which were based on durability, performance based on the scope of each design principle, and expected qualities outlined by FPL foreman. Durability. Although the rigidity and stability of the collar was far below expectation with an alternative method of manufacturing, which was originally 3D printing, the collar was a lot more flexible. Because of the base material used, plywood, the collar was 30S plywood. Performance. Performance in relation to climbing the pole was less than desirable. Although the actuators and motors did work, there were issues mounting it securely. Additionally, the Rupert collar did not have enough space to allow mounting in the given 90-degree open gap. Finally, there were many issues regarding the rotation of the outer collar section and the inner collar section. Friction between these sections was too high. Weight of mounted components increased said friction, and the angle which our outer collar section should have had was skewed due to human error during assembly. Expected qualities. The Rupert collar was too heavy for the specified 50 pounds upper weight limit. The collar itself without any mounted components was already 36 pounds. It was way too large and did not fold to be inside a handheld suitcase or a suitcase on the back of an FPL truck.
Hello, I'm Giancarlos Gomez, and I'm responsible for the hammer test subsystem. It consists of a gearbox enclosure which is capable of winding up, holding, and releasing a hammer. When the hammer is released, it creates an audible strike on the pole. However, the mechanism creates an unraveling wire noise. To solve this, we created a low-pass filter. The gearbox enclosure uses its own 12-volt battery source and communicates over Bluetooth because there is no way to wire it physically from the inner collar to the outer collar, since this is located externally. Placed on the outer collar, shown on the bottom left. We've had a multitude of issues with this due to the mechanical aspect of the design. The hammer test gearbox was implemented in the following manner. We had the DC motor attached to a solenoid using a custom part, as shown on the bottom left. A mini breadboard that contains the Arduino Nano, the Bluetooth module, and the connections as shown in the third picture. There's a 12-volt battery supply in there. There's a gearbox with 3-pulley system as shown in the second picture. And then in the next slide we can see there's a pivot point on the bottom which allows the hammer to move back and forward. For the hammer test, we created it by going into SOLIDWORKS and creating the design, then we 3D printed it. We didn't mount it to the collar because it was too heavy and it could have snapped the collar. The original plan for the collar was to have it 3D printed, but it was laser cut instead, which made it much weaker. And we were not allowed to reprint this gearbox enclosure, so we had to make do with what we had. The mechanical issue causing it not to function properly was also a concern for why we didn't put it on the collar. It would have been pointless to put it on if it wasn't going to work properly. Through manual aid of the motor alignment, we were able to achieve winding up, holding, and releasing. By using this method, we were able to grab some audio samples as shown below for the low-pass filter. The top one is the unfiltered and the bottom one is the filtered, and we can hear it here. And we can hear that the majority of the unraveling noise was filtered out. And as shown here, the crest factor came back as 19.5, which means it was in the bad range, and it did sound like a bad hit. So the low-pass filter worked successfully. For the testing, we took the gearbox enclosure to FAU and tested it on the wooden utility pole. We had the Raspberry Pi with the microphone placed under the collar to detect sound. We manually strike the pole by winding it up with the 9-volt battery and releasing the solenoid manually. Then we obtained results in the app for good and bad strikes. This hammer test subsystem also consists of a rotating collar design. There are supposed to be 3 gear spurs placed on DC motors that are of high torque, equally spaced in angles throughout the collar. The collar should rotate in a 360-degree motion, and we can see in the picture on the right that the gear spurs matches the teeth of the walls of the outer collar. We also had to manually create windows on both sides of the inner collar to allow the gear spurs to rotate. For the rotating collar design and the testing and the implementation, it was not capable of rotation due to high friction. There was significant gaps at the connections of each piece. This was resulted due to the laser cutter being miscalibrated, and we had to manually drill holes which made the alignment of the connections not match, and we had to file down components, which really created an issue and a lot of error. We also miscalculated tolerances since we swapped over to the laser cut design. The original design didn't need nuts, bolts, and screws, and this led to a lot of obstacles in the way for the collar to rotate. Also, the outer collar sags slightly inwards, and the gear spurs were not placed tightly onto the DC motors because they were a bit too wide and hard to get on it. I'm also responsible for the rechargeable battery subsystem. It consists of 2 heavy-duty drill batteries, and we mount them on to the adapter. These adapters are connected to DC buck converters, and these buck converters step down the voltage from 20 volts to 12 volts and 5 volts. The 5 volts are used for sensors, Raspberry Pi, etc., and the 12 volts are used for motors, actuators. There's also a battery percentage reader installed on the collar, on the inner collar, facing towards the pole. All the wiring was hidden inside the hollow portions of the inner collar. The rechargeable battery subsystem was implemented and tested in the following way. We ensured all the components were receiving the proper voltage by using a multimeter. We used electrical tape to secure the wiring inside the inner collar. We secured all the components inside the collar by using wood screws and drilling them to the collar itself. That way they wouldn't move out of place. We ran all the wiring through the windows throughout the collar and ended the wiring at a breadboard near the center of the collar. That way we can jump all the connections to the Raspberry Pi. The reason for this was that the Raspberry Pi couldn't be placed inside due to a multitude of metal being located throughout the collar, and it would pose as a hazard having metal touching the Raspberry Pi. Thus we decided to have the Raspberry Pi outside of the collar, and also it would make it easier for us to demonstrate the 3 DC motors that would have turned. So we placed 3 DC motors outside to replicate what would have happened, and the 3 DC motors that were placed inside the collar. It was also easier to troubleshoot and program the Raspberry Pi having it outside of the collar, because once it's inside, it's very hard to get it out. You have to disassemble the whole thing. And also, it allows us to move the microphone around freely, easily.
For the climbing and tensioning portion of our project, our initial plan was to use a set of DC motors and linear actuators to both provide tension and the proper lift to ascend and descend the pole for the system. We figured that using 3 such setups, a combination of the motor and actuator together, equidistant across the collar, would allow proper grip to the pole as well as the torque needed to lift the entire system up or down the collar safely. The actuators would automatically adjust during operation to ensure tensioning was maintained. Poles tend to taper as they get taller, so we would need the actuators to move to account for that, as well as any imperfections that may arise during the climb. We were going to achieve this through use of a force sensor providing feedback to the currently applied force of the linear actuator. We later changed that to measuring the motor current, which we'll explain in future slides. As far as implementation, we chose to use a dual shaft motor for the DC motor, as looking at notes from the previous team that tackled this project, they had a drifting issue due to the singular shaft motors they used, so this would allow us to keep a straight climb during operation. Due to issues we had placing the force sensors where they needed to be, as well as getting them to read the proper signal when force is being applied, we decided not to use them to provide the feedback. Instead, we decided to use a current sensor, which happened to be included on the motor driver board we were using to drive the actuators, that provided a current based on the ratio of the current going to the motor. That way we could get a rough estimate of the force being applied, which we'll explain later. There was a formula found that could be used. As of right now, using the mobile app, the motors and actuators move together, but in futures before the showcase, we plan on implementing a separate button to show them acting independently as they would during normal operation. As far as testing for this subsystem goes, the DC motors we used were merely tested to ensure that they would provide the torque we needed to lift the system up the pole and descend the pole safely. We also checked to make sure that they stayed in sync, and we had no issues there, so we didn't implement any sort of speed control. As well as when using the mobile app, there was no issue with signals reaching motors at different times, so they still stayed in sync. The issue we had with the load cells for the actuators was we had used half-bridge load cells, which were designed to be used two together, but we did not need that for this, and we were having difficulty reading a proper force being applied to them, as well as finding a way to position them properly between the motor and the actuator that would still allow a secure connection between the two. So we opted to remove that method. So without the load cell, we decided to use a current sensor to measure the amount of current being drawn to the motor. This allowed us to, using the formula seen at the bottom of this slide, along with some other specifications for whatever linear actuator is being used, you could get a rough estimate of the force being applied by the actuator. Now the issue with this as compared to the load cell was we need to constantly have activity in the actuator, as if the actuator were to turn off, the motor current would obviously also turn off, and there'd be no way to calculate the current force being applied. So this would mean we'd have extra battery being drained by the subsystem that we would not have had an issue with had we been able to properly implement the load cells like we had wanted to.
Alright, so I was responsible for creating the mobile app for this project. The mobile app was used in order to remotely control the collar. I created the app in Android, and it connects to the Raspberry Pi using Bluetooth. Buttons on the app interface send commands to the Raspberry Pi, and then the Raspberry Pi receives the commands and executes Python code accordingly. And that's essentially how the main control works. Hammer test results are sent from the Raspberry Pi to the app and displayed in the app. To initially test using the Bluetooth to control the Raspberry Pi, I connected a LED and used the buttons to turn it on and off. And to initially test processing of hammer test data, I sent placeholder results to the app before we actually had the hammer test system running to be able to test that out. Here's a general outline of the process I went through creating the mobile app. First, I designed the user interface. After that, I set up the Bluetooth communication. And this was done both in the app as well as in Python on the Raspberry Pi. And once a connection was secured, I tested it out by printing messages sent over Bluetooth. After that, I hooked up the LED and used the buttons on the app to control the GPIO, or general purpose I/O pins on the Raspberry Pi. And then I needed to create another visual interface to display hammer test results. And then I set up the database to store the hammer test results. And then at the end, I worked on combining the code of the caller functions to control other subsystems with the app. So to actually control the motors and the linear actuators and the hammer test system. And to store the hammer test results, I set up a database using Cloud Firestore from Firebase, which is a cloud-based database service. To organize the results, I added a prompt in the app to enter the ID of the poll. The ID is associated with the hammer test results when stored in the database, and users have the ability to view all the test results conducted in the current session. And when a user taps on a hammer test result, a prompt appears to ask them if they want to save the current test result to the database. And the users also have the ability to retrieve hammer test results by searching for the poll ID.
So for this project, I was responsible for the microprocessor system of the Rubic, the robotic utility inspection collar. We used a Raspberry Pi 4 in order to control the robotic collar. The Raspberry Pi was mainly used in order to contain our source code in order to be able to run all the different subsystems of the robot. These subsystems include the hammer test subsystem, the motor subsystem, the battery subsystem, and the overall movement of the robot up and down the pole. The microprocessor communicates with the mobile app via Bluetooth in order to execute functions. This was actually programmed by Ryan himself. He programmed it in a way where the Android app sent commands directly to the Python code that was created in order to execute the certain subsystems that I worked on. The microprocessor also contains the Crest Factor audio processing system, so whenever the Android app indicates it and the hammer test is run, the hammer test will obviously do its job, meanwhile also using the audio processing system. The audio processing system uses several different libraries, which we'll discuss in a little bit, in order to process the audio and then calculate the crest factor, which is used to determine whether or not the poll is a passing poll or a failing poll. Using the pin outputs on the Raspberry Pi, we are able to control the motor control, or we're able to control the motors, the hammer test, and the linear actuators in synchronization. So the motors will work in synchronization with the linear actuators if necessary, but we can also work all three linear actuators on our robot all at the same time. It's not that we have to move one at a time, they all move at the same time in order to climb the pole more effectively. So for project implementation, all software that we created was developed in Visual Studio's Code and Thonny. I developed majority of my stuff in Visual Studio Code. Ryan developed partially some of his stuff in Thonny via the Raspberry Pi. Within Visual Studio's Code, I downloaded several libraries, and on the Raspberry Pi, we downloaded several libraries such as PyAudio and SciPy. Many other libraries like NumPy, Keyboard, others that I can't really know off the top of my head were used for the audio processing and the other subsystems like the hammer test and the motors. The audio processing works by picking up a microphone, or by picking up sound via the microphone that we use, the high quality microphone, USB microphone. The audio is then developed into a numerical array, is transcribed into a numerical array, and then from that we create a .wav file using the WAV library. The .wav file is then processed via the numerical array to calculate the crest factor values. The crest factor values is actually a calculation that is used to figure out whether or not a sound is above a certain or below a certain frequency, and that is kind of how we determine whether or not this is a pass or a fail. The crest factor value is calculated using standard deviation and a calculation that is within our code. So in tandem with Ryan, we were able to implement the Python code for the motors and the audio processing system to work directly with the mobile application. So using the Android application that Ryan developed, we are actually able to control the entire robotic collar via Bluetooth with the Raspberry Pi. As soon as the Raspberry Pi is turned on, it is automatically running the script, and the Android device is able to connect to it via Bluetooth. All the motors and the actuators are controlled in real time. So what this means is that we don't have any preset buttons at the moment. Everything is run like a remote control, so the robot is remote controllable. We will have preset buttons that are already designed and coded, but we are just waiting to implement it via the app. So for project testing, the audio processing subsystem was tested via human hammer control strikes or hammer strikes on good and bad pulls to see what the crest factor values that we would result in. This is how we decided whether or not we were going to have a pass or fail range above or below a certain crest factor value. We ran several tests. We did several hammer strikes just to see what was the range of a good strike and what was the range of a bad strike, and we chose like a really good in between value. That was the good determining value. We've realized that a good hammer strike is going to be very distinct compared to a bad hammer strike. The sound is noticeably different by the ear, and whenever you see the results on the program, you can see that they are drastically different. So the pass or fail are, I would say, very accurate. But we did notice that because of the hammer test subsystem creating a lot of sound with the gears, we had to create an audio filtering system. The audio filtering system was designed and tested under loud background noise to see whether or not it still passed or failed under these conditions. This was a very difficult testing just because we didn't actually realize that the filtering filtered out the hammer strike substantially until I went through the audio samples and looked at them myself. This is why we implemented an audio amplification system which really filtered out all the background noise but kept the hammer strike, and it was the resulting was able to result in a good test for the hammer strike, a good audio sample. So I compared these audio samples from the non-filtered samples for testing and the amplified filtered audio samples, and when compared, the audio samples sound so much better without the loud background noise compared to the non-filtered. Now for the motor control, the wheels and the linear actuators, these were tested via the mobile app control after everything was wired. We tested our real-time movements via the Android app through the Python script to see how well it controlled the robotic collar. This was a very easy test. It was just to see whether everything was wired correctly and whether the wheels and the linear actuators worked. So some things that we learned. We learned that we should have used terminal wires to make sure secure connections in the wiring. One thing that we noticed whenever we were connecting everything during the build was that a lot of the wires tend to become loose very easily. So it's very difficult to really make sure that nothing becomes disconnected during testing or even during the during presentation. So we noticed that it would be best to use terminal wires just to make sure that everything is secure. We also learned that accounted for tolerances in the construction of the collars and the components that would be placed inside of them. So just making sure that you make sure that the total collar is durable and it is that everything, all the what it can tolerate is accounted for, just to ensure that there are no surprises in the end. We also learned that we should have used a DC motor with a long shaft in the connection for the gearbox enclosure to ensure that the gear always lines up with the gearbox. Currently, our hammer subsystem doesn't work as intended. That is why it is not attached to our collar, and that is due to not having a longer shaft on the DC motor. If we did implement it with a longer shaft, we should have not have ran into any issues there. We also learned that we should have went with the 3D collar design since the laser cutting did lead to a lot of assembly time and errors, and we obviously had a lot of issues with the FEU engineering team themselves with printing everything. So if possible, we highly recommend outsourcing printing if this project continues in the next semester. We also learned that it would be best to use linear actuators with force sensors already inside of them. The reason why we say this is because linear actuators without force sensors, it's very hard to actually automate the actuators without force sensors, because we can't actually tell how much pressure they're putting on the pole. Using force sensors, we would have been able to automate them on a pole, making it easier to climb up and down. This is a very good proof of concept showing that if force sensors are used, you could technically use the robot that we have with the sturdier collar to climb up and down the robot with it retracting and contracting whenever, or moving in and out whenever we climb a pole that is thick at the bottom but very thin at the top. Our recommendations for the future is making the range of poles covered smaller to obtain a smaller robot. So currently, with the instructions that we had a very wide range of different pole sizes, which resulted in a very big robot. Obviously, if we make these range of poles smaller, um, it would be a lot smaller, and it would cover a majority of the poles. The majority of the big poles can be covered with a bucket truck. Like when we spoke with our senior advisor, he told us that the bigger poles actually have certain trucks that we climb or that are used to actually go up and down the pole to test them. So we wouldn't have to deal with big, huge poles. We also recommend avoid laser cutting the wood unless it is really thick in all dimensions. It is not going to result in a sturdy robot, and you're going to run into a lot of issues. Make sure to pre-plan all the wiring and component placements. We did not plan this ahead of time. We kind of just placed things as we went. We did have a wiring schematics, but we did not plan the placement and how everything was going to be organized within the robot. Using a handheld device instead of a robot to examine the sound of the manual strikes made by the technician. The poles are only examined at the first 6 feet above the ground or the first half foot below the ground. Linemen can easily operate in this range. The majority of the rot is located on the underground portion of the pole, and the robot does not dig. So in the future, for maybe a project like this, have better specifications of what the project entails. Like we read here, the majority of the poles are examined in the first 6 feet, which any male or female of average height can reach that very easily. So having maybe just a handheld device with the audio process system that we have to examine the sound would be a lot easier than having an entire robot. We also recommend including striking points on the app to show in real time where the robot striked on the pole. This is a very more complex system to implement, but if possible, it could be used to show where the robot has striked in the future, to show in real time how the pole withstood the strikes and what effect it had to them. Another recommendation is using a different method of testing the pole. Should be used, since the collar turned out to be a large and heavy object. So it kind of goes with the previous, using the handheld device. A different method would be a lot better than using the robotic collar.
Alright, so here's the app. I'm going to start out by connecting to the Raspberry Pi with Bluetooth. Now it's connected, I'll enter in the pole ID, just a random one. And now it's ready to go.
Okay, so now we'll connect the 2 batteries to the collar that power everything. We have a battery display here that shows the current battery level. And so first Ryan's going to use the mobile app to extend the actuators, and when the actuators extend, the wheels move in the motion to lift the collar upward, and then he'll retract the actuators, which will cause the wheels to move in the opposite direction, simulating climbing downward. So I'll let Ryan do that.
So first I'll extend. And it goes as long as I'm holding the button. And then I can retract it the same way. Like that.
Okay, so the next thing is we'll simulate the hammer test. So we have these 3 motors right here that'll simulate the inner motors here you see with the red gears that would rotate this large outer collar. And then I'll be over on the pole swinging our hammer subtest to simulate the hammer strikes. And we have the microphone right here that'll be recording things. So whenever you're ready.
Alright, I'll start it now. you can see the test results showed up. It says 1 good hit and 7 bad hits, and the overall rating is bad. And if I go to view results, it'll show the results of all the tests from this session. If I tap it here, I can save it to the database. So now it's saved. And I can go back and keep controlling it.
Alright, so here we have the database in Firebase, and we can see that the test we saved is here. So go in here and it shows the number of bad hits, the date, the good hits, and the overall rating.
So here we can see the Hammertest subsystem having issues. Here's me winding it up manually and releasing it manually. Okay. And that is a manual strike. Hammertest subsystems had a multitude of issues due to the mechanical aspect of the design. And this is our team.